Hello everyone, my name is Kasha. I am the CEO of TechBlick. And what I would like to do today is to really give you an overview of many of the latest and interesting trends in the diverse world of printed, flexible, large area electronics. In particular, I would like to first focus on this trend of soldering on low temperature PET compatible substrates. And I'll look at many of the trends which are emerging that will enable this achievement. Next, I will look at the trend of the use of printed electronics in large area LED lighting. And then while we are on the topic of LED lighting, I will look at the trend or the potential use of printed electronics in MicroLED displays. We then look at how the resolution of printing processes are dramatically improving, both for digital printing, now achieving sub-micron or a few micron resolutions, and also for the latest roll-to-roll high-speed printing, achieving, let's say, 5 micrometer resolution running at 100 meters per second. We look at some of the applications, such as repair in displays, such as transparent antennas. Then we look at one of the hot trends in the world of printed flexible electronics, which is in printed electrodes and electronic skin patches. And I'll give you a few interesting examples of actual products and of actual success stories. We then say a few words about how stretchable inks have become really a portfolio business. So instead of just offering one stretchable conductive ink, now companies are offering a compatible set of stretchable inks, including adhesives and dielectrics and carbon inks and so on. But we then look at photovoltaics, and of course printing has a long history of trying to enter into the PV industry. Of course the bus bars and silicon solar cells are printed, but now again there is a renaissance, and OPVs are again gathering attention. They are sort of waking up again. And also there is very interesting work on scaling up the production of printed perovskites. There is work on inkjet printing perovskites, but what I will highlight today is work on actual roll-to-roll printing of perovskite PVs on ultra-thin flexible glass. We then look at the progress in roll-to-roll displays, in particular looking at electrochromic displays and how they've come very far, and now they can be produced roll-to-roll using screen printing at fairly high speeds. Printing batteries has always been a challenge, and most people use coin cell batteries, but now I want to highlight one innovation which I think has a lot of potential for solid state polymeric printable batteries, screen printed secondary batteries. We then enter this world of 3D or 3D shaped printing, be it printing of PCBs on various substrates, being truly printed, 3D printed electronics, be it metallizing a 3D surface, or being truly building up layer by layer a very complex 3D printed structure. We then talk about InMold Electronics, which, as I will say, is about to enter into real commercialization. We then talk about transparent heaters and say just a few words about the latest innovations in copper inks, and also the latest incremental but very, I think, important progress in silver nanoparticle inks. And then we finally conclude. So a kind of a wide-ranging tour of some of the interesting applications in the world of printed flexible electronics. But before I go into the details, just a few words about us at TechBlick. The way TechBlick works is that you can become a member for a year by buying a single annual pass. Once you become an annual pass holder, you have access to our more or less monthly live conferences on emerging technologies. And each of our monthly live conferences has about 45 to 50 hand-picked speakers bringing the entire value chain together. So from early stage startups to manufacturers to device makers, all the way to numerous end users and OEMs. You will have access to our fantastic networking opportunities. You become a member of our community. You can participate in all kinds of video-based global networking activities, and you can also engage with our ever-growing library of content, bringing you the latest from the field. And of course, one of our very important focus areas is printed, flexible, InMold hybrid textile electronics. And the two dates that we have announced, one is just a few days away, 10th and 9th of March, and the other one is on the 11th and 12th of May. So we really encourage you to consider becoming our members and to joining our very thriving community. So now let's go into the details. And actually here you can see a list of some of our exhibitors too. So let's go into the details. So the first topic is actually low temperature soldering. And if you think about flexible PCBs, you will notice that many of the flexible PCBs are actually based on a PI substrate. And part of the reason for this is that PI can tolerate a relatively high temperature, allowing automated reflow process of soldering. This is part of the reason. Of course, one can still solder on PET, but usually this is done manually. And the reason is that when it is done manually, one can much better control the temperature profile of the soldering process, making sure that it does not exceed the constraints of PET. However, now there is some very, very interesting approaches that allow one to solder on substrates such as PET. One of the interesting approaches is by our gold sponsor, Novacentrix. And what they do is they are bringing their pulsed lighting system into soldering. So you can expose the solder joints to a high dose, a pulsed dose of light, and that will allow it to form the joint without the actual substrate experiencing a high temperature. And what is even more interesting is that this process can happen if optimized, if the centering profile is optimized, can take place on a matter of milliseconds. So it means that you can really solder roll to roll at high throughputs on substrates such as PET. Another very interesting innovation here is shown in the middle of the slide, and this one is interesting because it is from the same, it comes from the birthplace of SAC 305 solder, so Iowa State University. And the company commercializing this is a startup called Safitech. And what they are developing is a SAC 305 microcapsulate solder that can be applied on a PET at just 120 degrees Celsius. So it is really interesting because it means that you can combine the properties of solder, including that automatic self-alignment, which eases the burden on the pick and place, so the pick and place doesn't have to be as accurate, with a low temperature substrate. And all of this means that flexible hybrid electronics becomes closer to reality, because you can roll-to-roll metallize, you can roll-to-roll pick and place, and also you can solder on substrates such as PET at fairly good speeds, but more importantly at low temperatures. But conductive adhesives are also experiencing a lot of interesting trends, and one that I like to highlight here is by Condaline. Condaline has a very interesting process. What they do is they use electric fields to vertically align or form chains of the fillers inside of the host. So the key benefit of that is that one can achieve an anisotropic conductive thermal or electric conductor without needing as much filler content. And it is often the filler that is the expensive part in these kinds of conductive adhesives. So one can cut down the filler amount by as much as, let's say, 80 to 90%. So here you can see an example on the right hand side. On the top side you can see the particles which are in the host dispersed at random, and in the second image on the right in the middle you can see that the particles have been aligned vertically under an electric field. So to reduce the amount needed for the same basically performance. And as you can see in the image below, this can come in the form of sheets. This is now done roll to roll. The thickness of the sheet can be variable per customer request, and also the pitch density is now excellent, and the process is now being scaled up. So I think it is something also to look into, because I think it's an interesting innovation that can help really drive down cost while exceeding or at least matching the performance of existing options. Another interesting trend is in printed electronics in large area LED lighting. And I think, of course, for quite some time, printed electronics or printed circuitry or metallization has been applied to LED lighting. And one of the key advantages, as you can see on the left, and this is by a company called Kundish, is that one can achieve customized patterns on the surface and then apply the LEDs on that customized patterns. So what it means is that one can have the shape or the geometry or the design that one desires using the printed circuit on the flexible substrate or on the large area substrate. Another interesting trend, and this has been around for some time, there were companies that started commercializing this maybe 4 or 5 years ago at least, but now it is gathering steam and momentum. It's doing everything roll to roll. So here you can roll to roll, print the metallizations and also the component attached materials, and also roll to roll assemble the LEDs onto your flexible conformable substrate, allowing one to have excellent throughput and an excellent production process for creating kind of flexible conformable LED foils. And so I think this is again an interesting area that one should keep an eye out. And this particular example that I've highlighted here is by Holst Center in Netherlands. But while we are on the topic of LEDs, I think one of the hot trends in the display industry is, of course, micro-LEDs. They are fantastic, but they're hard to manufacture. As you can see on the right-hand side, they come in many different forms, and they can be put to use in different kinds of displays, from small size displays, micro displays, all the way to very large area displays. And there are many methods of transferring the inks, transferring the LEDs, and so on. One point that is often neglected is that how do you metallize the actual substrate? So once the micro LEDs have been pick and placed or transferred onto your mother substrate, there has to be some metallization on the substrate. And this can be done by PVD, so you apply PVD, then you etch it, and then you have to create a connection between the front side of the substrate, so typically glass, to the back side by creating a via and filling that via. However, now companies are proposing that this metallization and also the connection from the front side to the back side be done using screen printing. And this is an example by Applied Materials. This comes out of their Italy group. And what you can see is that they are screen printing electrodes that wrap around the edge of the glass, connecting the front to the back side, and they're achieving a line width to spacing ratio of around 60 to 40 micrometers. And clearly the advantage here is that you don't need vias and you're doing additive printing. So I think a very interesting approach, and this is an engineering problem that is not, let's say, as sexy as the sort of the transfer problem, so it receives less attention, but it's equally important, and I think printing can play an interesting role here. But of course, transfer is a big problem when it comes to micro LEDs. On the left hand side, you can see that micro LEDs are very small. This chart shows you a comparison in size with, let's say, hair, which is relatively big actually compared to micro LEDs, to, let's say, atmospheric dust and viruses. And note the x-axis is actually logarithmic. And the chart on the right shows you the number of failed dies for a given yield at different resolutions, and the inset is kind of a blown up or a zoomed version of this. And basically, to achieve very few failed dies, the yield of the process has to be very high. And this is, of course, extremely challenging when one aggregates the yield across the whole process, including metallization, transfer, bonding, and so on and so forth. So there is a need to repair. And one opportunity that, again, printed electronics offers is precision digital printing on 3D surfaces. And again, here I want to highlight this very interesting company, XTPL, out of Poland. And what they do is they have a digital printer that can achieve, using their own viscous silver nanoparticle inks, very fine lines. So here on the top left-hand side, you can see examples where they've printed, let's say, a 3.2 line with a spacing of just 0.7 micrometers. And if you look at the bottom left-hand side, you can see examples of this technology being applied to create open defect repair in high resolution displays. Of course, this could be applied to MicroLEDs, but also other types of displays. This is really interesting because it shows how the resolution of printing processes are dramatically improving. Here on the right, you can see a benchmarking of this process against some other kinds of additive processes, including inkjet and aerosol and so on. And what is interesting is that here you can achieve very good feature sizes, very small feature sizes, and also have a good ink viscosity. So this is a process that, of course, is not just applicable to open defect repair in high resolution displays, but could be used in security, in prototyping, redistribution layers, in electronic packages, and in many other applications. But I think the trend towards better resolution is not just limited to digital printing. And I think I want to highlight here that also roll-to-roll printing is achieving resolutions which were uncustomary in the early days of printed electronics. I remember when I entered into this field about 10 years ago, one of my first exposures was to a company that was doing cutting-edge roll-to-roll printing, achieving a line width resolution of around 18 micrometers. Now this example by Kodak, again one of our sponsors, shows that one can do roll-to-roll flexo printing, achieving a line width resolution of 5 micrometers while running the process as fast as 100 meters per minute. And this is very interesting, and of course, as you can see on the bottom right hand side, some of the innovation has to do with the way they form their kind of master templates. And one of the key points here is that the way they manufacture it, the dots have an actual flat top. So a very interesting process in my view, with very interesting application. And one of the applications is in transparent antennas. And here actually, this is not a fully direct, additively printed approach. It is a hybrid approach, and you can see this in the bottom left-hand side. It is, it is hybrid because it involves ink patterning, flexographic roll-to-roll printing, and then the process goes through a roll-to-roll electroplating to metallize it further. But if you look at the table on the bottom right-hand side, you can see some very interesting parameters. So they are getting a metal mesh with a line width of 7 to 8 micrometers with a sheet resistance of just 0.66 ohms per square, and very good transmission, so transparency of about 90.5% at green, at 50 nanometers. And the application they were targeting is a transparent, printed transparent antenna, which the design of which can be customized to meet different requirements, including GPS and LTE and Wi-Fi and so on and so forth. So this is again an example of how the resolution and speed are improving. Sorry, let me just go forward now. So a very interesting hot area actually in printed flexible electronics is in medical electrodes, and there are many applications. One of the development frontiers has been in the use of electronic skin patches for continuous healthcare monitoring. And of course, this area has become extremely hot as we transitioned from, or as we are transitioning from, standard glucose sampling to continuous glucose sampling, and also all types of continuous heart rate monitoring, which are multi-billion-dollar businesses today. And printing can really play a role here. The example I want to highlight here is the development by Holst Center, and they've developed a full solution. This is a clinical grade disposable patch with reusable electronics with dry electrode, and the dry electrode includes printed metallization, and that allows one to measure ECG and respiration and temperature, and it is useful for 7 days continuous monitoring. So a full solution from the adhesive to the printed lines to the rigid electronics and so on. And I think it shows you what is possible with printed electronics. The examples on the right hand side are from another company, Screen Tech, again one of our sponsors. And what you find here is that they, on the top right side, the kind of the purple red picture, what you see is a medical electrode with integrated surface mount devices on the top. And the bottom right picture is an example of a screen printed sensor which can detect skeletal muscle activities. So you can see that all kinds of electrodes can actually be printed. And while we are on the topic of skin patches, a lot of discussion has also been on electronic textiles. And one of the, of course, the link or the overlap between electronic textiles and printed electronics is often the printing of the interconnects or the printing of the stretch sensors. In the early days, maybe 4 or 5 years ago, companies started to bring out their first generation of conductive stretchable inks. And now what's happened in the last, let's say, 2 years or so, is that companies are not just offering stretchable conductive inks, but they're offering the full portfolio of stretchable inks needed to create your electronic textiles. And this includes, of course, the silver ink, but also the carbon ink, the dielectric ink, the conductive adhesive. The example I've picked here is from Namix, one of our sponsors. So you can see they've got a silver ink that can be stretched by 100% and achieves less than 200 microohms per centimeter. They've got a carbon ink, and they've got even a very good adhesive. And if the chart in the middle shows you the properties of the adhesive, it can be stretched up to 30% with very little hysteresis. And also it can be cured at 80 degrees Celsius. And I think the adhesives are very, very important in the full system. And the chart on the bottom right hand side, I've picked this because it shows you that if you only had a silver printed ink, the resistivity would be lower, so a more conductive layer, compared to when you had a stack printed, a stack composed of silver, carbon and dielectrics. But when you have a stack, you are making it more washable. And in this case, you can see that after experiencing 100 washing cycles, the material or the stack of materials has performed better. It has experienced a smaller amount of change in the overall resistance. So back to this topic of electrodes actually, and what I want to highlight here is that this is a fairly big business. Just by showing you one example, this is from Mekoprint out of Denmark, again one of our sponsors, and the example you see on the right hand side is a roll-to-roll screen printed ECG electrodes, and this application has a volume sales of more than 100 million units per year. And the example I'm showing on the left hand side I think is also very interesting. This is an incontinence sensor. It is again roll-to-roll screen printed, and the reason this is interesting is that here conductive carbon lines are actually roll-to-roll printed on a stretchable non-woven material. And again, this is a commercial application, and the printed sensor is part of a full solution including the rigid electronics, the communications and so on and so forth. So we can see that when it comes to electrodes, there is already demand for skin patches. Similarly, roll-to-roll printing is there to meet the volume demands, and companies are really developing full solutions. So when we are talking about roll-to-roll printing, I just want to highlight this example of electrochromic displays. Electrochromic displays have been around for quite some time actually, and in the early days the production was manual and it was very slow. But now the company Invisible has actually roll-to-roll, made the process roll-to-roll. So here you can see an example of the roll-to-roll machine, and the whole process is roll-to-roll. So the printing, the conversion, the testing, everything can happen on the roll-to-roll machines. So they screen print all the 6 layers needed for the electrochromic display, and everything is roll-to-roll. And of course this is helping bring down the costs, meet volume demands. And one recent application which was announced just a few months ago is the application shown in the middle here, where the electrochromic displays are used in the tag that is continuously monitoring the conditions of the minced meat as it goes through the value chain. So very interesting, and actually Invisible is now able to take customers from the R&D and the design phase all the way to pilot and volume production as a single one-stop shop supplier. So while I was talking about electrochromic displays. I came to this in progress in printed batteries, and the reason I've chosen this is because of the example on the bottom right hand side. So if you look at this example, you've got an NFC charger on the left side, you've got an electrochromic display on the top side, and in the middle you've got a fully printed battery, a secondary battery. And this can provide enough. In a few seconds you can charge it up and then drive your electrochromic display. Very interesting innovation in my view, because it is a UV curable polymeric solid state battery. The company Evonik, one of our sponsors, supplies you the screen printable slurries that you can print as part of your own production process to meet your own design and geometry requirements. There are no toxicants involved, and it is a secondary battery. So I think it is solving some of the key pain points in the industry. And of course, we all know that the industry has been using coin cells, even though printed batteries have been available, with of course some very good exceptions. Printed batteries are commercialized, have been commercialized, but many have shied away and used coin cell. But I think this is really an interesting development in the industry. So again, while we are on the topic of roll-to-roll, I want to show you an example of a full inline integrated roll-to-roll system integrating both digital and analog processes. This one is by Kotema, and it's really interesting because it has everything in one machine, from the winder to the roll-to-roll slot die to dryers to laser patterning to rotary screen printers to inkjet to inline inspection to cooling. So you can see that one can have almost a roll-to-roll foundry in a box system. So on the right hand side you can see kind of examples of the different elements of the machines used at different stages of this inline. And Kotema is a fantastic company with many years of experience, of course, in the field, and they allow you to do prototyping and testing of inks and concepts on their machines. And they have a deep and long-standing experience in the field. At the start, I mentioned that printed electronics and photovoltaics are of course very closely linked. We know that printed bus bars are used in solar cells, and this is already a huge application. And people tried to also print organic photovoltaics for many years. And the peak, the honeymoon, was when Konarka was around. And some of you guys may remember Konarka, the American company. They raised well over $100 million, and in the end they failed. They hyped up the industry dramatically, they overpromised. And after the failure of Konarka, the industry went into this long period of just wilderness. It was lost. And it kind of lost the attention to perovskites, because perovskites were demonstrating a very fast growing efficiency. But I think OPVs are again on the cards, they are on the agenda, and they are kind of suddenly again showing rapid improvements in efficiency. So the chart here was supplied to us by Brilliant Materials out of Canada, and it shows you the materials that are being developed to further improve the EQE or the PCE of the OPVs, or organic photovoltaics. Also, there is a shift in the from fluorine to non-fluorine acceptors, which is accelerating this trend. And also, there is a lot more production know-how now in the field. So companies are transitioning to wider format printing, faster printing, and they're much better able to control the morphology of the printed acceptor donor mixture on the substrate. What is also very interesting in my view is the example on the right hand side. This is EMC, I think they came out of Kodak, and what they are doing is they are trying to scale up the roll-to-roll production of perovskites. They are printing on a flexible 100 micrometer glass. So the picture in the middle is showing you how they are printing the metal mesh on a 100 micrometer flexible glass. In this example, they were able to run at up to 60 meters per second, but of course the whole process is a little bit slower. As you can see on the right hand side, they are going from a roll-to-roll pilot line to a very large scale machine. And the idea here is that they want to do it on a 1.5 meter web. running up to target is 30 meters per second. And if everything goes well, this could be a big application for flexible glass, a big success story for roll-to-roll printing, creating a 4 gigawatt roll-to-roll printed or coated perovskite factory. Of course, there is a lot of development to be done, but nonetheless, this shows you the kind of the intent and how far these companies have come. So now let's talk a little bit about 3D printed electronics. And this is also a very interesting area. And I think, roughly speaking, one can divide it into two directions. One is metallizing an already 3D shaped substrate. So the top row shows you examples of this. Here you can see a metallization of an antenna on a 3D shaped substrate. You can see examples in the automotive, in a heater, and also in a medical device. And there are many other applications. Of course, the antenna printing was the biggest one, but now I think more are coming. And the row at the bottom shows you examples of actually 3D printed electronics, where printed electronics is being combined with classic 3D printing to create circuits and SMDs, surface mounted devices, inside and outside of a 3D printed object of a very complex shape. And here you can see examples where the parts have been integrated into a kind of a dice, or they've been integrated into an egg shape. And I think this is really interesting because it allows one to really bring intelligence to 3D printing. So instead of just creating dumb mechanical objects, one could integrate also the electronics inside the 3D printed object. And if one has a seamless design to production process, it could open up many fantastic opportunities. And one good example here is a company, Neotech, from Nuremberg in Germany, and they have some of the best machines in the field. So if you're interested in machines, please check out Neotech. So PCB printing, of course, PCBs are etched, they're not printing. But I think one trend that started maybe again 4 or 5 years ago and is now beginning to mature is actually printing the PCBs. And one example is the company from Canada, Volterra. They have a desktop printer that allows you to print the conductive lines. So you supply it with a Gerber file and it prints the metallization lines. It can create the vias, it can deposit the solders or the conductive adhesives, and it can also go through the reflow process. And this can be done, as you can see in the applications on the right hand side, on a whole range of substrates. So, FR4-like substrates to flexible substrates. And very interesting, almost a desktop all-in-one turnkey solution with many applications in prototyping, for R&D research centers, for groups trying to design various kinds of circuits and try it out, and also, of course, for a university. So this is, I think, another trend that should be watched as it is beginning to mature. So InMold Electronics, this has been a story of start and stop and start and stop. I think the big story many years ago now was Ford accepted the overhead console made using InMold Electronics, but then had to recall the product because there were defects. But the development continued behind the scenes, and then a few years ago, applications, small-sized InMold electronic applications in wearables and consumer devices appeared. Then we had applications in InMold Electronics for creating heaters embedded into the cover glass of LED lights for cars, so to accelerate the defrosting. And now I think we've reached a point where we can expect very soon applications actually in the interior of cars being made using InMold Electronics. So this process has come a long way from developing the entire material set, developing the very complex process, which has had a very steep learning curve for the industry, printing all the layers needed, thermoforming it, curing it, and before or after placing the SMDs and the conductive adhesives and the connections and then overmolding. It's a fairly complex process. But now there is a built-up experience in the industry. The industry is able to handle complex design, integrate lighting, integrate various functionalities in the InMold Electronics. So I think this is a trend that is really taking off. But I want to show that 3D shaping and stretching and kind of applying functional layers is not just InMold Electronics. A very good example is by Kimoto, one of our sponsors. And they have created this 3D formable diffusion film. You can see this on the right hand side. This is IMD, InMold decoration. And the idea is that you have this film, as you can see at the bottom right. It can be stretched up to 200% into an arbitrary shape that you want. And here, this is a light diffuser, and the purpose is shown on the top right. So instead of having, LED light is discrete, and it looks discrete. It doesn't look like a continuous lighting. But by applying this 3D formable diffusion film, one can achieve a kind of an excellent distribution of light, and also the film is able to dissipate heat well, and so to hide a lot of the heat hotspots. So very interesting, I think, approach. Printed transparent heaters, excuse the pun, but really a hot area, because there are not so many good solutions out there for printing transparent heaters. And a lot of the solutions that are emerging involve printing. So one approach is to embed very, very fine trenches inside of the substrate, place your seed layer and then electroplate, so that you end up with very fine but deep embedded copper lines, highly conductive into your substrate, and achieve very, very good results over large areas with very fine metal mesh features. So having both very low conductivity and very high transparency. Another approach is by a company, Chasm, out of Massachusetts, United States, and they have their own material, which I believe is a combination of silver nanowires and carbon nanotubes, which can be screen printed. And when you screen print it, as you can see in the example at the bottom, you can create a heater that goes to, I believe, 120 degrees Celsius or beyond. And actually you can see an example on the right hand side where this film has been applied to a front headline of a car, and you can see how the temperature profile has actually increased. It's really an interesting solution because it is an excellent heater and it is also transparent. Of course, the story of printed electronics and copper are intertwined, and conductive inks are intertwined. And for many years, people have tried to create copper inks to replace the expensive silver without so much success. And there have been two major problems. One of them has been the curing without oxidization, so special equipment or conditions were required, often adding experience, and also making copper not a drop-in replacement. And another problem has been that copper wasn't conductive enough, so you would end up printing such a thick layer that you would make your cost benefits disappear. Now there are some coppers appearing on the market which seem very promising, and one example I want to highlight is by Cupprint out of Israel. And you can see their own benchmarking. This is not my benchmarking, this is a benchmarking done by the company itself, but you can see here an example of conductivity versus sintering time of their copper in comparison to a range of nanoparticle and other types of inks. It is a process that you print it, you dry it, and then you do a very rapid sintering to achieve very, very high conductivity. And their latest material actually compatible with, typically the sintering process is, let's say, 200 degrees Celsius, but they also have a process which allows one to sinter at 160 degrees Celsius or so, so compatible with, let's say, potentially heat stabilized PET, and achieve 6 milliohms per square per mil. And on the bottom left hand side, you can see a range of emerging applications. So paper-based roll-to-roll manufactured RFID tags, automotive seat heaters. Copper has been applied on anodized aluminum substrates, which are used as the board in LED lighting, in two-sided PCBs, in transparent display boards, and also there have been some tests with fairly good results on metallization of some types of silicon photovoltaics. And of course that market is the biggest market for printed conductive paste. But the story of development is not limited to copper. Also, silver nanoparticles, now not a new technology, they've been around for well over a decade, if not much longer, this technology is now in the phase of incremental improvements. But those incremental improvements are nonetheless very, very important. And I want to highlight one example by Agfa. Agfa actually also acquired recently the assets of Clarion, so now they have solvent and water-based silver nanoparticle inks in their portfolio. This example I'm highlighting is actually the two charts show you the same thing. One of them is zoomed in and the other one is zoomed out. It shows you that for a given curing temperature, the achieved conductivity has dramatically improved. So in particular, look at the case when the curing is just 110 degrees Celsius. You can see that the latest generation of inks are achieving much better conductivity, much lower level of resistivity. This is very important development because it pushes silver nanoparticles towards low temperature processing. It widens the scope of available substrates. And for a long time, people were complaining that when you have a sort of an annealing temperature constraint and your substrate cannot handle the temperature, the challenge is that you don't get enough conductivity. So these developments are really trying to address that. So a very important progress. I think, printed electronics for a long time, for decades, was about membrane switches and human machine interfaces and capacitive switches. I just want to quickly highlight that even in these areas, the industry is not staying stationary, is not at a standstill, and is making really good progress. So here are three examples. On the left, you can see just a customized membrane switch keyboard with integrated USBs. In the middle is a capacitive keyboard with an integrated controller. And on the right is an integrated touch sensor with a display driver. Basically, the message here is that companies making HMIs, membrane switches, and capacitive switches are trying to integrate and are integrating more higher value and complex steps into their printing process. So they're integrating, let's say, a USB system into the membrane switch and so on and so forth with printed circuitry. So basically, migrating towards the value add as the membrane switch itself becomes or has been a highly commoditized business. So this brings me to the end of the presentation. I hope you enjoyed the tour of kind of applications existing and emerging in the world of printed flexible electronics. We went from low temperature soldering to LED lighting to MicroLEDs to precision digital printing to roll-to-roll precise printing to 3D printed electronics, OPVs, perovskites, heaters, carboning, silvering. So really a wide-ranging tour of many of the applications in the world of printed flexible hybrid electronics. Again, I'd like to just remind you guys, we at TechBlick offer a very interesting model where you can become a member, or as an individual or as an enterprise, for 1 year. You can have access to all of our live conferences for a year. They take place every 4 to 6 weeks. We handpick the best kind of companies, from startups to OEMs in the fields. Our focus is on emerging technologies, and one of our biggest areas of focus is printed flexible electronics. And as part of our portfolio of live events, live online events, we have 2 dates dedicated to printed flexible electronics, one on 10th and 11th of March and the other on 11th and 12th of May. So if you have any questions on that, reach out to me at kasha@techblick.com. Otherwise, thank you for your attention and thank you.